Good day and welcome back. This will be our first video discussing the cross product. So as a reminder, in the previous video, we explored our first concept of a vector product, something called the dot product. And what we saw was that the dot product of two vectors, as long as they have the same number of entries, is going to end up being a number. And furthermore, we introduced a bunch of related properties. With the cross product, we're going to take the same approach. We're going to begin by defining the cross product of two vectors. And then from there, we're going to build up to some properties, explore some examples, and finish with an application. But hopefully throughout the next few videos, you will see kind of the similarities and the idea that we're just paralleling that previous discussion. Okay, so to start off with, we say that if A is a vector with three entries and B is a vector with three entries, then the cross product of A and B is a vector. So immediately we see a difference compared to the dot product. And we define A cross B as follows. So notationally, it's just A and then this time symbol. And in words, it's A crossed with B is equal to the following vector. So A2B3 minus A3B2 for the first component, A3B1 minus A1B3 for the second component, and then A1B2 minus A2B1 for the third component. So we get this nice, very simple definition of the cross product. And because you can't see me here through the computer screen, I should indicate that I'm being just a touch sarcastic. This is just a key example as to why we don't want to try to memorize each and every formula that we encounter. And in a few minutes, we will give a more methodical way to remember this formula for the cross product. But first, let me make some key observations that immediately distinguish this from the dot product. So the first thing I want to note is that this is only defined for vectors with three entries. So this would be vectors in V3. And the key thing is only. With the dot product, all that was required is that both of the vectors have the same number of entries, whether that's 2, 3, or 17. Here, the cross product is only for vectors in three-dimensional space. And furthermore, if you were to spend a few minutes studying this formula, we could ask, what is the relationship between A cross B and B cross A? And it turns out that they're not equal to each other, but they are opposite of each other. So if you switch around the order that you're taking the cross product, it has to be balanced out with this negative. So another difference compared to what we saw with the dot product. Furthermore, if you were to calculate A crossed A, that is, in our above formula, if each of these B's ended up being A's, think A2, A3 minus A3, A2, all of these components would be 0. So what you would get back is not just 0, that's a number, you would get back the 0 vector. So now in terms of computing the cross product, it turns out that determinants can be very helpful to do this efficiently. So let me kind of remind you how determinants are defined. And I use the word remind you lightly here because you may or may not have encountered these in previous or other courses. So in order to define the determinant, we do so in a sense kind of using an iterative process. We start off with a 2 by 2. So we think we have this matrix whose entries are from left to right, A, B, C, D. To calculate a determinant, what we do is we multiply together the entries on that main diagonal. So that would be A times D. And then we subtract away the entries on the cross diagonal. So we subtract away B times C. So that's for a 2 by 2. We can do the same thing with a 3 by 3. So we're thinking we have all these entries, typically numbers, but they could be functions or other types of quantities. So D, E, F, G, H, I. So how we go about this is as follows. we are going to work our way across the top row. So we start off with this A entry. And we're going to have A, and then we're going to multiply it by a 2 by 2 determinant. And how I get that 2 by 2 determinant is I cross off the row and the column that A is in. And when you do that, what remains is this 2 by 2. And we are going to multiply by the 2 by 2 determinant that is there. So what we would multiply by is EFHI. And as we work our way across the top row, there's going to be a pattern, plus, minus, plus. So I'm going to indicate that with just a plus, minus, plus above. So when we get to that second entry, it's going to be minus B. And we're once again going to multiply this by a 2 by 2 determinant. And it's the 2 by 2 determinant that would remain when we cross off the row and the column that contain B. And we can see from inspection here that would be the 2 by 2 matrix given by D, F, G, and I. So that would be D, F, G, and I. Then when we go to that third entry in the first row, it's plus C, and we multiply by that 2 by 2 matrix that remains when we cross off the C row and column. So D, E, G, H. So we calculate a 3 by 3 determinant by breaking it down into 3 smaller, easier to compute 2 by 2 determinants. And something you might be wondering at this point is, what in the world does this have to do with the cross product? Well, let me tell you. So A crossed with B is going to be a 3 by 3 determinant. The top row is going to be made up of those standard basis vectors we previously encountered, I, J, and K. The second row is going to be A1, A2, A3, the A vector. And the third row is going to be B1, B2, B3, the B vector. So if we were to write this all out using our above formula, we have I times that kind of resulting 2 by 2 determinant when we cross off the I row and column. So that would be A2, A3, B2, B3. Remember the pattern, and this is key, plus, minus, plus. So when we cross off that J row and column, we have A1, A3, B1, B3, plus K times A1, A2, B1, B2. And I find this to be the preferred method, opposed to trying to memorize some formula that we might very easily mess up and not realize. And this is a point where if we are in class and we are working face to face, I would suggest that we take 3 or 4 minutes, turn your desk, work with your neighbors, and see if you can compute the cross product of the vectors given here by A and B. So go ahead, pause the video and take a few minutes and see if you can calculate that cross product. Oh, and hopefully at this point you've taken a few minutes and you've come up with a computation for the cross product. And just to make sure we're all on the same page, A cross B can be computed as a 3 by 3 determinant. So remember, we put I, J, K across the top row. The vector A goes across the middle row, and the vector B across the bottom row. So we would have I times the 2 by 2 determinant given by 2, 0, 3, 1. The pattern is plus, minus, plus. And the key mistake I see with the cross product is forgetting that minus with the middle component. So be careful. Minus J times the 2 by 2 determinant 1, 0, 0, 1, plus K times the 2 by 2 determinant 1, 2, 0, 3. And if we put that into a vector, the first entry is going to come from that I component. And we're going to have 2 minus 0. So remember, with that 2 by 2 determinant, we multiply down the main diagonal. We subtract what we get when we multiply down the cross diagonal. In the middle component, we're going to have minus the quantity 1 minus 0. The minus sign coming from that minus in front of the J. And our third component from the K is going to be 3 minus 0. So we end up with the vector 2, minus 1, 3. And similar to the dot product, we see that coming up with the computation of what the cross product vector is not necessarily difficult to do computationally. It certainly will feel tedious at times, but it doesn't have a high level of difficulty associated with it. So the question that now remains is this vector we get back, what does it tell us? So in the next video, we will explore properties related to the cross product. So stay tuned and take care.